Hello everyone. So today we are back again with a new topic, that is mode of failure. So moving on to the topic. So first we have to know what is theories of failure. Okay. So let me go through it. What is theory of failure? Okay. In the previous, it has been discussed that how the state of stress can be determined for any point in a component subjected to combined loads, and how to get the value of maximum principal stresses and maximum principal shear stress developed in the component. Okay, so now for designing components subjected to combined load, it is important to relate this complex state of stress to the properties of material, yield strength, ultimate tensile strength, percentage elongation, etc., which we get in the stress strain curve, okay, for ductile materials. So for this, it is important to relate this complex state of stress to the properties of material like yield strength, ultimate tensile strength, percentage elongation, etc., which are obtained from the simple tension test, so that the failure in such conditions can be predicted. This relationship is provided by theories of elastic failure, okay, which are discussed in the next slides. Okay, so first we go through maximum principal stress theory. Okay, so this theory is also known as Rankine's theory. This is why, because this theory is credited to W.A.J. Rankine. Okay, so this maximum principal stress theory is also named as Rankine's theory. Okay, it states that failure of any mechanical component subjected to complex state of stress occurs whenever one of the three principal stresses equals or exceeds the strength. That is, whenever maximum tensile stress exceeds the uniaxial tensile strength, or maximum compressive stress exceeds the uniaxial compressive strength. If sigma 1, sigma 2 and sigma 3 are the three principal stresses, with sigma 1 greater than equal to sigma 2 greater than equal to sigma 3, theory says that to avoid failure we have to follow this relation, that is sigma 1 less than equal to SUT and sigma 3 greater than equal to minus S of UC. Okay, therefore design equations based on maximum principal stress theory can be written as sigma 1 is equal to SYUT divided by FOS, that is factor of safety, and sigma 3 is equal to minus of SUC divided by FOS, that is factor of safety. Okay, next we can view in this figure. It is a figure failure envelope based on maximum principal stress theory. Okay, so this figure shows the failure envelope based on maximum principal stress theory. Okay, for plane stress case, sigma 2 is equal to 0. Okay, so area is bounded by lines. Sigma 1 is equal to SUT, sigma 1 is equal to minus SUC, sigma 2 is equal to SUT, and sigma 2 is equal to minus SUC. This is the relation. Okay, so test data shows that this theory is suitable for predicting failure of brittle materials and is not recommended for ductile materials. Okay, next we move on to the next theory, that is maximum shear stress theory. Okay, so this theory is also known as Guest and Tresca's theory. Okay, so this theory is credited to C.A. Coulomb, H. Tresca and J.J. Guest. So maximum shear stress theory is also known as Tres and Guest theory. Okay, so this theory states that any mechanical component subjected to any combination of loads will fail whenever maximum shear stress exceeds shear strength of the material, that is shear stress at the time of yielding in the standard specimen of tension test. Okay, so I will show the figure in the next slide, where figure shows Morse circle for three-dimensional stress with sigma 1, sigma 2 and sigma 3 as principal stresses, such that sigma 1 greater than equal to sigma 2 greater than equal to sigma 3. So three principal shear stresses are then given by this relation, okay, that is tau 1 2 sigma 1 minus sigma 2 by 2, tau 2 3 sigma 2 minus sigma 3 by 2, and tau 1 3 is equal to sigma 1 minus sigma 3 divided by 2. Okay. Next, here you can see the figure of Morse circle for 3D stress. Okay. So as evident from this figure, maximum shear stress is tau max is equal to tau 1 3 sigma 1 minus sigma 3 divided by 2. Here it is. And next is tau max is equal to tau 1 3 is equal to sigma 1 minus sigma 3 divided by 2. Okay. Now, for simple tension test, sigma 1 is equal to sigma x and sigma 2 is equal to sigma 3 is equal to 0. Giving tau max is equal to sigma 1 divided by 2. Okay. Also, yielding in simple tension test starts when sigma 1 is equal to S of yt. Therefore, maximum shear stress at the time of yielding in simple tension test is tau max is equal to S of yt divided by 2. Thus, design equation based on maximum shear stress theory can be written as tau max is equal to Syt divided by 2 into f of s, and sigma 1 minus sigma 3 is equal to Syt divided by f of s, that is factor of safety. So here in this figure you can see failure envelope based on maximum shear stress theory. This is sigma 1, sigma 2. So S of minus Syt minus Syt, this is 0.0. Okay. Note that for plane stress case, sigma 3 is equal to 0 and tau max will be equal to sigma 1 minus sigma 2 divided by 2. Graphical representation of maximum shear stress theory giving failure envelope for state of plane stress, that is sigma 3 is equal to 0, is shown in figure. According to this theory, for state of plane stress, yielding starts when sigma 1 minus sigma 2 is equal to Syt. But in first and third quadrant of this sigma 1 minus sigma 2 plot, sigma 1 and sigma 2 are of same nature with sigma 1 minus sigma 2 greater than sigma 2, and yielding may start when reaches the yield strength Syt. Okay. Therefore, in first and third quadrant, area is bounded by lines sigma 1 is equal to plus minus S of yt and sigma 2 is equal to plus minus S of yt. Whereas in second and fourth quadrant, area is bounded by lines which represent the condition where maximum shear stress reaches the shear strength of the material. That is, tau max is equal to S of Sy is equal to Syt divided by 2. Okay. This theory is suitable for predicting failure of ductile materials but is a little conservative. Next, moving on to the next theory, we have maximum distortion energy theory. So, this theory is credited to M.T. Huber, R. von Mises and H. Hanke. Okay. So, this theory is also known as von Mises theory. Okay. So, maximum distortion energy theory can also be written as von Mises theory. Okay. So, maximum distortion energy theory states that a mechanical component subjected to combined loads fails when the distortion strain energy per unit volume at any point in the component reaches or exceeds the distortion strain energy per unit volume of standard specimen of simple tension test at the time of yielding. Okay. So, this theory gives a value of equivalent stress called von Mises stress, which is defined as the value of uniaxial tensile stress that would produce the same level of distortion energy as the actual stress involved. Okay. So, this is given by the equation, that is sigma von Mises is equal to square root of sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square divided by 2. Okay. So now, to avoid failure of the component, this von Mises stress should not exceed yield strength of the material. Therefore, design equation based on maximum distortion energy theory can be written as square root of sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square divided by 2 is equal to S of yt divided by factor of safety. So here you can see the figure of failure envelope based on maximum distortion energy theory. Okay. So this figure shows the failure envelope based on maximum distortion energy theory for state of plane stress. Experimental results have proved that this theory is the best suitable for predicting failure of ductile materials. It can be proved that according to maximum distortion energy theory, yield strength in shear is 0.577 times yield strength in tension, that is SYS is equal to 0.577 S of YT. Okay. So with this we have come to the end of this lecture. Thank you everyone.